Hello and Assalamualaikum everyone. So in this video, we're going to continue our lecture on Markovian queuing models, where we're going to move on to a more specific type of birth-death process known as the single server queue and also the multi-server queue. Okay, so in our general birth-death process, okay, so it is mentioned there that each of the mean arrival and also the service rate can take any non-negative value. Okay, so therefore we have basically a great flexibility in modeling a queuing system based on the birth-death process. Okay, so the first model that we're going to look at is we're going to assume that these queuing models have a Poisson input, hence having an exponential inter-arrival time, and also have a Poisson service, which basically means it has an exponential service time. So the first model that we're going to look at is called the MM1 queuing model. So it has a Markov or exponential arrival and service process. It has one server. Okay, so M here refer to Markov service process. Okay, this is arrival. This is Markov service. Okay, so basically it also means exponential, and this is your number of server equals to 1. Okay, so there are no limitations on the waiting line or the number of customer allowed in the system. Okay, so these are the condition, okay, or the definition for MM1Q. Okay, so by looking into our transition diagram in figure 3.2, okay, so the arrival rate, okay, for the customer is lambda, okay, for all state, okay, and then the service rate is mu, okay, for all state as well, starting from state 1. So this is basically your mu1, mu2, mu3. So this is your lambda naught, lambda 1, lambda 2, and so on. Okay, so we have the same value because you have only single server. So when you have one customer in the system, okay, so the server will begin working and the service rate is mu. So you have two customers, so one customer is being served, you have one customer waiting in line. Okay, so this basically is the transition diagram for your I equals to 1, 2, 3, okay, until some value n, continuing to infinity. Okay, so next what we're going to do is we're going to write our rate matrix for our queuing model. Okay, so for the rate matrix you have your state. Okay, so let us write until state 3. Okay, so the diagonal element is the negative of the leaving rate. Okay, so for 0, so the rate of leaving state 0 is lambda, so the value of your diagonal element is negative lambda. Okay, so for state 1, the leaving rate is lambda plus mu. Okay, so the negative value. Okay, the same for state 2. Sorry. The same for state 2, negative lambda plus mu. Also for state 3 and so on. Okay, and then jumping from state 1 to state 0, okay, the rate is mu. From state 2 to state 0, so you don't have any rate. Okay, and then jumping from state 0 to state 1, basically your arrival. Okay, so you have your lambda. 0 to 2, okay, nothing, so it is 0. So then from state 1 to state 2, okay, so we have lambda and then 0. From state 2 to state 1 you have mu. State 2 to state 3 you have lambda, okay, and then state 3 to 1 you don't have any value. State 3 to 2 you have mu. okay, and then continuing like that. So basically it only has three, you have diagonal element, okay, and then you have this value here, this value here, okay, which is the same because you have a single server and the same arrival rate for all state. Okay, so next, okay, using the balancing probability flow, okay, we're going to write down our equation. Okay, so the first equation we will have lambda pi naught equals to mu pi 1. Okay, our second equation we will have lambda plus mu pi 1, sorry, equals to lambda pi naught plus mu pi 2. Our third equation we will have lambda plus mu pi 2 equals to lambda pi 1 plus mu pi 3. Okay, and if your I is equals to n, which is the more general term, so you will have lambda plus mu pi n equals to lambda pi n minus 1 plus mu pi n plus 1 and so on. Okay, so for your I equals to 1, 2, 3 and so on. Okay, so next let us take our first equation. Okay, so our first equation gives, okay, so the purpose of this is we want to express our pi naught in terms of, sorry, pi I in terms of pi naught. Okay, pi I in terms of pi naught. So our first equation will give us, okay, pi 1 equals to lambda over mu pi naught. Okay, so then our second equation we have pi 2 equals to lambda plus mu pi 1 minus lambda pi naught over mu. Okay, so substituting this into here, okay, you will have lambda plus mu, okay, you have lambda plus mu pi naught here minus lambda pi naught over mu. Okay, so simplifying this, you should be able to get lambda over mu square pi naught. Okay, so by the same way, so for pi 3 you should get lambda over mu to the power of 3 pi naught. Okay, so continuing this, we can basically postulate that for pi I, it is equals to lambda over mu to the power of I pi naught. Okay, so we can prove this by using proof by induction, but it is basically not covered in this course. Okay, so next what we're going to do is we're going to determine the value of pi naught. Okay, after we express our pi I in terms of pi naught, okay, what we can do is we can try and solve for the value of pi naught. Okay, so in your notes, it is a much simpler way to determine the pi naught, but I'm going to explain a way so that we can get a clearer picture, okay, where we're going to try to find the pi naught, okay, by using the sum of the probability. Okay, so the sum of probability is equals to 1, okay, so which will give you rho to the power of I pi naught equals to 1 because we substitute our rho equals to lambda over mu, which is also our traffic intensity. Okay, so next we're going to factorize or take out our pi naught. Okay, I equals to 1 infinity pi I, rho I. Okay, and then our pi naught is actually equals to 1 over the summation of rho I. Okay, so how we're going to get this value is by using the sum of geometric series. Okay, so the sum of rho to the power of I for I equals to 0 until infinity is equals to 1 over 1 minus rho. Okay, which gives you 1 over rho as the value of your pi node. Okay, so in your node, so basically in order for you to determine pi node, it's just that by looking at the proportion of the time the server is busy. Okay, the server is busy at all state except state 0. You have a single server. When your customer arrives, the system is in state 0, your server will begin its job and then being busy. Okay, the server is only idle at state 0. Okay, so hence you can just basically calculate your pi node by considering the proportion of the time the server is busy, the same as your lecture node. So that's why you get straight away 1 minus pi node equals to rho, which gives you the value of pi node equals to 1 minus rho. Okay, so after we have determined the value of pi node, so basically this gives you, okay, the probability of being in state I equals to rho to the power of I 1 minus rho. Okay, so you substitute, okay, for your I equals to 0, 1, 2, and so on until infinity. Okay, so your rho here is equals to lambda over mu, which is your traffic intensity. Okay, so next we're going to look into the measure of effectiveness, where we're going to find the value of LC, LQ, WC, and also WQ. So first up is our LC. Okay, so what is LC? It is the average number of the customer in the system. So LC is equals to the summation of I equals to 0 until infinity I pi I. Okay, so substitute your pi I. So you should get I rho I to the power of pi node. Okay, right? So then your pi node is equals to 1 minus rho. Okay, so you can take out 1 minus rho here. So you are left with I pi I, sorry, I rho I. Okay, so if I interchange the symbol, please follow my writing. Okay, so it should be I rho I. Okay, so if you were to expand this term, so you should get rho plus 2 rho square plus 3 rho cube and so on. So factorizing rho, you are left with 1 plus 2 rho plus 3 rho square, okay, plus 4 rho cube and so on. So 1 minus rho times rho, okay, and then we're going to simplify this term into summation. So you will get summation of I equals to 1 until infinity I rho I minus 1. Okay, so this value over here is actually the derivative for the summation of I equals to 0 until infinity rho I with respect to rho. Okay, so from there we can continue. So we should get, okay, using the sum of geometric series again, okay, the summation of rho I is equals to 1 over 1 minus rho. Okay, so by differentiating this term, okay, we will get 1 minus rho times rho times 1 minus 1 minus rho square. Okay, and then you can cancel out your 1 minus rho, so you should get rho over 1 minus rho. So this is equals to your LC. Okay, so your LC is equals to rho over 1 minus rho. Okay, so your rho is lambda over mu. So if you're asked about the average number of customers in the system of MM1, so you just substitute the value of rho over 1 minus rho. Okay, so next we're going to look at our LQ. Okay, so our LQ is the average number of customer in Q. Okay, so LQ, we start our I equals to 1 until infinity because you have a single server. So I minus 1 pi I. Okay, so let us expand this term. So I equals to 1 until infinity I pi I minus I equals to 1 until infinity pi I. Okay, so this term, okay, is actually the same as the summation of I equals to 0 until infinity I pi I. Okay, because when your I is equals to 0, the first term became 0. So it is basically the same when you start your I at 1. Okay, so the second term remains I equals to 1 until infinity pi I. Okay, and then your first term is actually equals to your LC. Okay, and as for your second term, okay, it is actually equals to the complementary event 1 minus pi naught. Okay, because the sum of pi I is equals to 1. Okay, so since you start your summation at I equals to 1, so basically this is equals to 1 minus pi naught. Okay, so then you can just substitute your LC, which is rho over 1 minus rho, and then minus your pi 1 minus pi naught. Okay, so simplifying this, you should get rho square over 1 minus rho. So that is the value for your LQ. Okay, so now that we have determined our LC and also LQ, we can use our Little's formula to determine our WC and WQ. Okay, so remember Little's formula, L equals to lambda W. So for your WC, okay, you just take LC over lambda. So rho over 1 minus rho over lambda. So you can substitute your lambda equals to rho mu. So you should get rho over 1 minus rho times 1 over rho mu. So you can cancel out your rho. So you should get 1 over mu 1 minus rho for your WC. Okay, so next let us calculate our WQ. So WQ is equals to LQ over lambda. Okay, so rho square over 1 minus rho over lambda. Okay, so which is equals to rho square over 1 minus rho, okay, times 1 over rho mu as well. Okay, so you can substitute in order for you to simplify. Okay, so you can just use the term lambda as well. Okay, so it's up to you, but this term is much more simpler. So you get rho over mu times 1 over rho. So this is your WQ. Okay, so basically for MM1Q, we will have our LC equals to rho over 1 minus rho. Our LQ equals to rho square over 1 minus rho. WC equals to 1 over mu 1 minus rho. And WQ equals to rho over mu 1 minus rho. Okay, so these are the measure of effectiveness for MM1Q. Okay, so let us look at example on how we're going to try and solve for this. problem. Okay, so customer arriving at a local burger drive-through takeaway. Okay, so let us look at the information. The number of cars arriving in given interval follows a Poisson distribution with mean of 24 cars per hour. So the average time taken to serve a car is exponentially distributed with a mean of 1.25. Okay, let us extract the information. First, we need to determine our lambda and also our mu. So lambda is our arrival rate. So 24 cars per hour. Okay, so 24 cars per hour basically means, okay, if you were to use the unit minute, okay, you should get 0.4 per minute, or you can use 24 per hour as well. Okay, depends on the unit that you want to use. I'm going to use minute, so make sure for your inter-arrival times also you use, for your service time also you use minute. Okay, so for your service time, average time taken to serve a car is exponentially distributed with mean of 1.25 minutes. So your mean is actually 1 over mu. So your 1 over mu is 1.25. Okay, so which gives you your mu equals to 1 over 1.25 equals to 0.8 per minute, or you can use the unit hour. Okay, so next we can calculate our traffic intensity, lambda over mu, okay, which is 0.4 over 0.8 equals to 0.5. Okay, so let us look at question A. So what does it want? Okay, so the probability that there are no cars at the drive-through at all at any given time. So what do we have to solve for question A? So probability that there are no cars. So basically your system is in state 0. Okay, so state 0, probability no cars refers to your pi node. Okay, so calculate your pi node, which is equals to 1 minus rho. Okay, so question B, the average number of cars waiting for service. So average number of cars waiting in queue. Okay, so that is the value of LQ. And then question C, the average waiting time for service. Okay, so that refers to your WQ. For D, the average time spent by a car in the system. So that refers to your WC. And then question E, the average number of cars in the system refers to your LC. So just substitute the value here. Okay, so we have our lambda 0.4, our mu 0.8, and our rho 0.5 in our formula that we derived earlier to get the solution to question A up until E. Okay, so that is all for MM1 queuing model.